Okay guys, this is 21.1 Aerodynamics project hosted by University of Luxembourg. I'm Paolo Scuderi, I'm 25 years old and I'm from Italy, and I studied at Politecnico di Torino University and the Von Karman Institute for Fluid Dynamics. My mate is Benet Eiximeno Franch, he's 23 years old, he's from Spain and he's a student of Universitat Politècnica de Catalunya Barcelona Tech.
So in this presentation we are going to cover all the points related to the scope of our project, especially analyzing the effects of the geometry, the effects of the Reynolds numbers and the effects of the turbulence models in the simulations. So the driver is a, let's say a generic car body developed by the Technische Universität von Munich. And yeah, there's like lots of configurations for these cars based on these three different geometries that change in the rear end: the fastback, stateback, and notchback. And basically we focused on reducing a little bit the computational cost to make it feasible for these two mods. And we decided to go for the configuration that had no wheels, but it included the rear view side mirrors.
In fluid dynamics problem, we would like to solve the Navier-Stokes equation, which are analytically unsolved to their nonlinear quadratic convective term. Therefore, to obtain a solution, we have two different strategies: experimental or numerical investigation. The first one is very expensive, while the second one is the so-called CFD. It is increasing thanks to the research activities in the HPC and on innovative numerical methods. In our problem project, the fluid regime is incompressible and turbulent. The turbulence is directly predicted by the Navier-Stokes equations. It is associated with the presence of three-dimensional vorticity and dissipation at the Kolmogorov microscales. Turbulence treatment does not provide a unique solution. In practice, when the Reynolds number is very high, the Navier-Stokes equations are highly sensitive to limited variation in the initial conditions. Hence, turbulence requires to be accurately modeled. To make it, there are alternative approaches based on the level of accuracy that we want to reach. This sketch shows which are the increments in the computational cost associated with a more elaborate numerical solution. In our work, we use Ran's equation. However, if you are interested, in one of my blog posts, I explain the different approaches.
As any other CFD simulation, we have been working on three main steps: the pre-processing, the simulation, and the post-processing. We have been working in the pre-processing on our local machines, and this step is basically dividing the whole domain into different volumes in which we are going to compute the flow variables. Then we had to run the simulations that we did in the IRIS cluster of the University of Luxembourg, making use of OpenFOAM. And finally, we post-processed all the results using ParaView, mainly on our local machines, but we also used that sometimes the cluster to connect. So when doing the meshes, we tried to perform several meshes to find which was the most appropriate for the results, and we compared it with experimental data obtained for the fastback geometry. So basically we did these two comparisons of a coarse mesh of 8 million elements and a fine mesh of 46 million elements, and we could see that the fine mesh had a different wake resolution, so still the coarse mesh was not good enough to resolve this area. However, when analyzing the pressure data on the symmetry plane of the car, we could see that both data converge a lot to the experimental data, which meant that our model was robust. So when looking to the final mesh, here we could see the distribution of elements around the whole car. It's important to see that we focus a lot on the boundary layer because we wanted to resolve this area much better because it is where there are more gradients. And here there are three refinement areas, each of ones with a smaller element length. So then for the simulations, our main simulations were incompressible and we used Ran's models. We wanted to compare these four. Right now we are still waiting for some simulations of these polar almaras, so we hope that we can present them in the report. And then here we also studied several details of the flow. We used the simple foam solver for the steady state and pimple foam for the transient, which still we must say that we have the right configuration, but we still have it in the queue and it's taking a bit more than expected. We had a script called run.sh that made the work of running all these open form settings?
First of all, we focused our attention on the coefficient of pressure. It is positive when the flow is decelerating, while it is negative when the flow is accelerating. Comparing the three different geometries, we can note a similar CP distribution for all the front areas. Instead, in the back, the effects of the geometries need to be taken into account. In particular, looking at the right part of the slide, we can see that for the fastback and the notchback configuration, there is the presence of two recirculating bubbles in the XY plane. These recirculating bubbles modify the structure of the wake. On the left side, we see the XZ plane where, for all the configuration, there are two main recirculation vortices. For fastback and notchback shape, they are located in the region nearest the wall and their width is smaller than the eastback one. On the right side, we put in evidence the effects of the geometry for fluid streamlines flowing near the rear mirror. Again, we can remark what was just explained before for the eastback version. In these slides, streamlines are mapped out. The biggest size of the wake vortices is associated with the eastback configuration. Instead, the smaller is related to the fastback shape. We will see in one of the next slides what this implies in the aerodynamics track. An advanced post-processing is the computation of the Q-criterion. Splitting the gradient of the velocity field in two matrices, one symmetric and one antisymmetric, we can compute the scalar Q value as written in the left part of this slide. When it is positive, we are considering area of higher vorticity density rate. The pictures show the isosurfaces for Q equal 10. On that, the velocity magnitude was plotting. The size of the vortices structure in the wake region is bigger for the eastback configuration, while for the fastback and the notchback the structure is similar enough. However, for all the bake shapes, no edge variation in the velocity magnitude are shown. In this part of our work, we analyze the effects of the Reynolds number, which is a typical dimensionless parameter used to express the ratio between the inertial and the viscous forces. Instead of changing the velocity boundary condition, we change the kinematic viscosity to obtain three different Reynolds numbers. Plotting our results, we perceive the independence of the CD value from the Reynolds number. This is a typical behavior of all the blunt bodies at high Reynolds number after the so-called subsonic crisis of resistance, in which the CD decreases suddenly as shown in the theoretical graph on the right. Finally, for the fastback configuration, we analyze the effects of different turbulence models. Plotting the slice in the wake region for three different x coordinates, we observe that only the k omega differs from the others. The ky predicts well far from the wall, while the k omega estimates correctly near the wall. Instead, the k omega SST is the combination of both. The wake region is a free zone far from the wall. For these reasons, we can point out these divergences in the slice. However, the best results are computed for the k omega SST.
So regarding future work, basically, well, first we would like to see the transient simulations that we have on the Q, but also analyzing different solvers, different turbulent models, starting with TAS and LES, and also introducing more complex details in the geometry. Well, thanks for watching our video, and if you have any kind of doubt, we will be really happy to answer it, and yeah, I hope you enjoy it.